All right, guys, so we are back. The first part of the video was focused on relative age, so the second part is going to be on absolute age. So you can see right here on the right side, it does say younger and older. That's the more of the relative age. But now you can see on the left side as we go down, exact ages of rocks. So we have to talk about how you go about determining what the exact age is. So absolute age is exact age. So, how do we determine it? Well, we use something called radiometric dating. Basically, what radiometric dating is it's measuring an amount of material in the rock. Okay, so there are atoms, which we'll get into in chemistry, but there are atoms present in the rock. Okay, and that the rock starts off with a certain number of those atoms. All right, over time, those atoms are going to break down. Okay, so if we know how much it starts with, and then we find this rock, and it doesn't have as much as it started with, but we knew how much it took to break down, we can determine how old it is. Okay, so the parent material is the beginning material. It's going to break down. As it's breaking down, it's actually forming something called daughter material, which is a different substance. I know this sounds like a lot of stuff. I'm going to show you some diagrams that hopefully will help. All right, so to do this, we use something called half-life. We calculate this radiometric dating using half-life, and that's the amount of time literally it's going to take for something to divide in half. Okay, so if I know the half-life of the parent, I can calculate absolute age. And an example is carbon-14 has a half-life of 5,730 years, which means if I start off with, let's say this is my rock, okay, my nice little soap bottle, this amount, and I start here, and I come back 5,730 years, there should be half of this bottle. Okay, that's what it basically means. You will be given half-lives. You're not expected to memorize half-lives. Carbon-14 is only kind of important to us because it is something that we have carbon in, so you're going to see carbon-14 dating used in fossils, and we're going to get to fossils in the next section. So here is a graph to kind of help you understand what I'm talking about. The red material over to the left is the parent material, and that's carbon-14. Okay, so we see 100% or 80 grams, 100% of the carbon-14 in the rock or the fossil, whatever it happens to be. 5,730 years have passed. I should only have 40 grams there, because it's going to break down in half. So it breaks down into, the parent material breaks into 40, but as those molecules broke down, they actually turned into something else, which is nitrogen. That's the daughter material, okay? So the red is the parent, the blue is the daughter. So as the parent is breaking in half, the daughter is increasing in amount, okay? So if I'm a scientist and I look at 17,190 years and I'm like, oh wow, this fossil has 70 grams of nitrogen in it, and I know it has 10 grams of carbon, and I'm like, wait a minute, I know how this is working out. I can calculate time, and I can calculate how much it had based on these numbers, okay? Another way to look at it, this is a little simpler of an idea, but we literally have a parent. We start off with 100% of the parent. After one half-life, so some set amount of time, I have half the parent, and I have half the child, okay? After another half-life, I'm going to have half of that half of the parent, and I'm going to have more of the child. So you can see from the beginning to the end, my parent is breaking down in half, my child is getting larger. Okay, they're kind of both occupying the same space. So we have to imagine that all together, it has to be 100%. So 100% of the parent is first. If I only have 50% of the parent, I have to have 50% of the daughter. If it's 25%, then I'm going to have 75%. Okay, do you see how this is breaking down? In the simplest of terms, all it means is by knowing where this is. So if I find the rock in this stage, and I know it started at this stage, I can work my way back and calculate time. And that's kind of all half-life is going to be. And we'll do some calculations in class to actually give a feel of how you go about calculating half-life. All right, index fossils. So in all of this discussion of time and understanding relative and absolute age, we're going to start working our way into fossils, but it's a good time to sort of bring up what an index fossil is. So an index fossil is going to be found within rock layers, and it's going to be used to help tell time, okay? It's kind of one of those time elements that we can use. So an index fossil is a species that has lived a short period of time. So it's lived a very short period of time and is unchanged, okay? And these are some key terms. So it's abundant, which means it's found all over the place, or it's multiple in the area. Widespread geographically means it's found all over the place. It's very distinct, and it's very limited in the time, in the geologic time, okay? So it's not like I find it now and then 10 million years from now, and then 10 more million years from now, and then 10 more million years from now. It's only going to be found in a block of time, but it's found all over the planet and all the continents usually, and it's abundant within the continent that it's in, but it's something that stands out, okay? And an example of one of these is a trilobite. So a trilobite kind of looks like a horseshoe crab a little bit, but it is which is actually probably right here. That's a trilobite. That's an example of an index fossil. But their presence in the rock, the presence of these index fossils are used by scientists to help date the rock layers. So if I know trilobites were abundant and widespread 65 million years ago, then the rock I find them in, I can guesstimate is probably somewhere in the 65 million year range. And so that's kind of what index fossils are used for, to help us with age. All right, so finally, kind of a term that sort of brings all of this together is the term uniformitarianism. So James Hutton, a long time ago, James Hutton is sitting here thinking, you know, there's all these processes on the planet that are happening, and people used to think that these processes just took 1,000 years. Okay, that's not the case. So Hutton was thinking, you know, I think the Earth's a lot older. I think the processes that form the Earth just take a really long amount of time. And so what he started to think was, and what he started to observe based on what he's seen looking around, geologists getting in the dirt, looking at the rock layers, what he comes up with is that the processes that are going on today are the same processes that went on 65 million years ago. So these processes do not change just because we've gone 100 million years in the future. They just take a really long amount of time to actually do. So uniformitarianism really means similar today processes are the same as the ones 65, 100 million, 200 million years ago. So if you have any questions, please make sure you see your teacher. Do not forget to take your notes check at the end of this, and come to class with any questions and ready to work on the age of rocks and fossils.